CMOS inverter pair, the delay is dependent on which transistor is on, either whether it is the nMOS transistor or the PMOS transistor. Now, when the input is 1, the nMOS transistor will be on. And as we have seen previously, the RS value for a sheet resistance value for the nMOS transistor, for the N diffusion transistor will be 10K, and the delay will be RS into delta CG. That here it is 2 delta CG, because the input will be connected here. The input will be connected to two transistors, nMOS as well as the PMOS. So it will have to see two gate. So two gate capacitances means 2 delta Cg. So Rs into 2 delta Cg, that will result in 2 tau. Similarly, from this stage here, here input is 1, hence the output will be 0. If the output of this stage is 0, in this stage PMOS transistor, the pull-up is on. When the pull-up transistor is on, the Rs for a P transistor, as we have seen, is 25K. This Rs into again 2 delta Cg, that is here this value will be 2.5 Rs. If this is 1 Rs, if we consider this to be 1 Rs into 2 delta Cg, this will be 2.5 Rs into 2 delta Cg, that is 5 Rs delta Cg. Then totally when you add these two, it becomes 7 Rs delta Cg or 7 tau. Here Rs is 10K, and here this value is 25K. If 10K is just taken as 1 Rs, then 25K can be just taken as 2.5 Rs. Here it is 1 tau, and this, sorry, 2 tau, here it is 5 tau, totally it is 7 tau. Next, coming to the CMOS inverter delay, there will be an asymmetry in the pull up and pull down, because of the difference in the RS values of pull up and pull down transistors. This difference can be reduced by increasing the channel width, but as the channel width increases, the capacitance also will increase. Next, coming to the raise time estimation, the output voltage across a capacitor will raise. The output will raise when input is 0. When the input is 0, the pull-up transistor is on. The pull-up transistor will allow current to flow through it, and it will charge the output capacitance CL. This pull-up transistor is, if it is a CMOS transistor, the pull-up network will be a P transistor. So current, assuming that P transistor is in saturation, current through the P transistor IDS is beta P by 2 VGSP minus VTP whole square. And we also know that the current in the capacitor I is C dV by dt. Now again, because here capacitor is getting charged by the current flowing, due to the current flowing through the P transistor, IDSP is the output capacitor is CL, D output voltage is V out, d V out by dt. Let VTP equal to 0.2 VDD, then and VGSP equal to minus VD, that is gate voltage is 0 minus the source voltage VDD, it is minus VDD. Substituting these two values in this first equation, we get IDSP will be equal to beta P by 2 0.64 VDD whole square. Equating this equation, that is the this VDSP as well as this VDSP, both of them are equal. The same current flowing through the P channel, it is charging the capacitor. So these two equations, current equations, are same. Equating that, that is here it is C dV by dt. dV means V2 minus V1. V2 initial voltage is 0. It is charging to VDD or V out. So it is V2. V2 is the final voltage V out minus initial voltage 0. The charging time, that is tau r, minus raise time, or it is the raise time tau r minus 0. So from this, finally we get tau r is 3 CL divided by beta P into VDD. On the same lines, we can also calculate the fault time estimation. Fault time means capacitor now discharges. Capacitor will discharge when input is 1 and nMOS transistor is on. When nMOS transistor, it is acting as a sinking circuit. that is, it is discharging the output. In that case, again, on the same lines, assuming that N transistor is in saturation, we know this will be the equation. Again, IDSN, the discharge current, is nothing but C dV by dt, and substituting VTN as 0.2 VDD and VGSN is equal to VDD. Substituting in the first equation, we get VDSN is beta n by 2, 0.64 VDD whole square. Now again equating this IDSN as well as the second equation, this IDSN and this equation, because both the current are same, and finally we get that falling time. Falling time is 3 into CL divided by beta n into VDD. Now from the above two equations, we saw that falling time depends upon beta n and rise time depends upon beta p. These two are the first two equations. Now, when we take the ratio of the first two equations, we see that tau r, rising time by to the falling time ratio, is nothing but beta n by beta p. We know that beta n and beta p depends upon the mobility of the charge carriers, and nMOS has a better mobility than PMOS device. The mobility mu n is equal to 2.5 mu p. Therefore, beta n will be 2.5 beta p. Beta mu n is 2.5 mu p, 2.5 mu p. Therefore, beta n is equal to 2.5 beta p. Comparing this, when we are substituting it here, we see that the rise time is slower than the fall time. Fall, that is, output falls when it is discharging to N transistor. N transistor has a better mobility, so falling happens quicker than raising voltage getting raised. So raise time is slower compared to the fall time. But if you have to achieve both symmetrical values, then the width of the transistors have to be made. That is, the width of P transistor should be equal to 2.5 the width of the N transistor. And also we see that the rise time and fall time will be proportional to 1 by VDD, or it is inversely proportional to VDD, and it is proportional to the capacitor, load capacitor CL. Now, suppose we have to drive large capacitive loads. Large capacitive loads means when signal has to be propagated from the chip to off-chip destination, that is on chip to off this outside the chip. If the signal has to propagate, then it is like driving a large capacitive load. Usually, this capacitive load will be much higher than the gate capacitance. If you have to drive large capacitance, then the delay will be more. So to decrease the delay, resistance has to be decreased. And we'll have to find circuits where the delay can be reduced. The solution for this is, we have three solutions, that is using cascading inverters as drivers, using super buffers, and using bi-CMOS drivers. By using these three, the delay can be reduced when we are propagating the signal from on-chip to off-chip destinations. First, coming to cascaded inverters as drivers. As I was telling you, if we have to, the load capacitors usually will be very high. So now we know that delay is nothing but R into C. So now if we have to decrease the delay, the option would be to reduce the resistance. And if we have to reduce the resistance, either decrease the length or increase the width. We cannot decrease the length beyond certain value. So the next option would be to increase the width. But as we are increasing the width, the capacitance increases and the area occupied will also increase. So instead of using a single capacitors like this, we cascade inverters here, so that we gradually increase the width. If we see here in this inverter circuit here, the first inverter, it is 4:1. The ratio, the length is to width is 4:1. And for the second inverter, if we see, the ratio goes as 4:f. And for the third one, the ratio is 4:f. square. The width ratio is gradually increasing from one transistor to another by a factor f. It goes on increasing. So as a it as a width goes on increasing, the delay is reduced. Thus, inverter tends to drive large capacitive load, and therefore this inverter should have low pull-up and pull-down resistances. As the width factor increases, the capacitive load, uh, that is the capacitive load present at the input, will increase, and it will occupy more area. The rate at which the width increases will influence the number of stages which are cascaded to drive the particular load capacitance. The delay of an inverter stage is function of the ratio of external capacitance to its input gate capacitance. That is what external capacitance it is driving to its internal gate capacitance. And the overall delay will be the sum of individual propagation delay. And the number of stage, that is how many stages has to be there, will get decided by the ratio, where we have this ratio y equal to CL by delta Cg, which is equal to f to the power of n, where f is the width and n is the number of stages. And then if the number of stages is too large, then the delay will increase. And if it is too small, then the fan out for each stage becomes a dominant factor. And here delay per stage is given as f into tau for delta V in, where delta V in indicates that is input is going from 0 to 1. When input is going from 0 to 1, that is when you are giving input 1 to an inverter, pull down is on. Pull down is N transistor. So it is 1 delta. So it is the width into this delta value. And for when the input is going from 1 to 0, that is when you are giving a 0 input, the pull-up transistor is on. Pull-up transistor means the delay will be 4 tau, and for a width of f, that is if the width is f now, it is 4f tau. And as I said, this number of stages is given by the ratio CL by delta Cg. Taking the ratio ln on both sides, logarithmic value on both sides, ln y will be equal to n ln f. So n will be, the number of stages will be ln y divided by ln f. Then by using the number of stages, we can see that the width gradually increases and the delay also gets decreased. So the next option would be to use super buffers. Super buffers are used so that the asymmetry in the delay, that is, we saw that the rise time and fall time are not equal. To remove that asymmetry, these super buffers are used. The first super buffer is inverting super buffer. In nMOS inverting super buffer, when the input is 1 here, Vin is 1, then this same Vin is connected to T4. This is also on. This is directly Vin. When Vin is equal to VDD, the voltage given here is also VDD. Input VGS will be VDD, and output will be quickly driven. The output will quickly go to 0. And suppose Vin is 0, the value at the voltage at this point is VDD, because this transistor is on. This point is driven to VDD, and the same VDD is given to V3 as well. T3. Since the VGS value is VDD here, the that is, we know that the drain current will be proportional to the gate voltage. More the gate voltage, more will be the drain current. Since now the gate voltage is almost equal to VDD, very high value, the drain current will also be high, and it will quickly charge the output capacitor. So the raise time will also increase. The fall time is anyway high, the raise time will also increase because the current IDS is more, because VGS will be more. Similarly, we have non-inverting type. In non-inverting type, the